So, in the last lecture we were examining the decay of a pulse, okay, a concentration field due to a pulse injected along the particular plane which is z is equal to 0. So, we are considering a plane in perpendicular to the z axis, okay, a one dimensional problem where there is no variation along the planes perpendicular to the z axis. The concentration diffusion equation for that case was this one. Okay, the concentration diffusion equation for that case was this one. And at t is equal to 0, we injected a finite mass per unit area in that particular plane. Okay. We had injected a finite mass per unit area in that plane. The concentration was effectively infinity because the finite mass is being injected into an infinitesimal thickness in the z direction. Okay. And then we were trying to examine what is going to be the concentration profile as diffusion takes place and this mass spreads in the z direction. So, the diffusion equation was the usual diffusion equation for one dimensional transport, unsteady diffusion equation for one dimensional transport. The boundary conditions was that concentration has to be 0 at plus or minus infinity, okay, because very far away from this plane there should be no mass of the solute because it has not yet spread over there. And at t is equal to 0 there is a finite mass that is injected. The mass that is injected initially has to continue to remain there for all later times. The mass injected initially has to continue to be in that domain for all later times because there is no production or consumption of mass in this case, and therefore, I have an integral relation for the total mass which is valid for all time. The integral of the concentration over the z coordinate has to be equal to the total mass per unit area that was initially injected. Okay. So, that is the condition on the total mass. Once again, this is an infinite domain, therefore, there is no length scale. So, we had postulated that we can use a similarity transform. Okay, we had postulated that a similarity transform will apply in this case. However, the concentration had to be scaled differently because what is a constant here is not the concentration at a particular location, but rather the integral of the concentration over the entire z coordinate. Okay. And the scaling for the z coordinate is square root of dt. Okay. So, therefore, the concentration had to be scaled by this mass per unit area divided by this length scale which is square root of dt, okay, at time t. Therefore, I defined the concentration scaled concentration as the concentration divided by square root of dt. Okay. So, using these two scalings we had done chain rule for differentiation to express the z and t derivatives in terms of derivatives with respect to psi, substituted that into the equation and got an equation for the concentration C star as a function of psi. We got an equation for the concentration C star as a function of psi, and then applied then solved the equation to get a Gaussian distribution, okay, what is called a Gaussian distribution, and then applied the boundary conditions and the integral condition to find what is the total concentration field, okay, to find what is the total concentration field. So, this function is also a special function, it is called a Gaussian function. Okay. So, I will just briefly go through what is a Gaussian function. Okay. The normalized Gaussian function is usually written as the normalized Gaussian function of psi of any variable. So, I will call it as x, okay, is equal to 1 by root 2 pi e power minus x square by 2. Okay, that is the normalized Gaussian distribution. And this has the following properties: integral minus infinity to infinity dx times g naught of x is equal to 1. It is normalized. Okay. Integral minus infinity to infinity dx x times g naught of x is equal to 0, okay, because this is a symmetric function. Okay. So, if I draw the Gaussian distribution, okay, g naught of x versus x, you will get what is called the bell shaped curve. Okay. This you will get what is called the bell shaped curve, which is symmetric about x is equal to 0. Okay. The left and the right sides are symmetric about x is equal to 0. It is finite at x is equal to 0. So, at x is equal to 0, if you calculate this term here, okay, at x is equal to 0, the exponential is 0. So, you get 1 over root 2 pi as the value at x is equal to 0. It is about 0.4 roughly, and it decreases as x goes to plus or minus infinity, okay, in such a way that this integral, which is the total area under this curve, has to be equal to 1 for a normalized Gaussian distribution. Okay. And this normalized Gaussian distribution also has unit variance. Okay. It also has unit variance, that is integral minus infinity to infinity dx x square times g naught of x is also equal to 1. Okay. So, the Gaussian distribution has unit variance as well. Okay. X square times g naught of x has to be equal to 1 for the Gaussian distribution. Okay. Usually the general Gaussian distribution is not expressed with unit variance, but rather it is often written as g of x is equal to 1 by root 2 pi into sigma into e power minus x minus mu the whole square by 2 sigma square. Okay. That is the general Gaussian distribution. Okay. The square root is only on 2 and pi. Okay. And this is also normalized, okay, minus infinity to infinity dx g of x is equal to 0. Okay. So, I plot this distribution, the maximum of this distribution will be at x is equal to mu. Okay. The maximum of this distribution will be at x is equal to mu, okay, not at x is equal to 0. So, it does not have 0 average. Okay. This distribution does not have 0 average. The average of this distribution is equal to dx x times g of x is equal to mu. Okay. And the variance of this distribution, okay, integral minus infinity to infinity dx x square times g of x will be equal to mu square plus sigma square. Okay. So, this is the general Gaussian distribution, okay, that is often used. Okay. So, the solution that we have is a form of Gaussian distribution. Okay. The solution that we have is a form of Gaussian distribution. The solution we had for the concentration C star, right, is equal to or let me take C itself. Okay. C is equal to m by 2 root pi dt e power minus z square by 4 dt. That is the general distribution that I have, and to get it to Gaussian form, I have to do the transformation. Okay. I have to do the transformation that the term in the exponent here has to be x square by 2. Okay. So, I have to do a transformation where I write z star is equal to z star square by 2 is equal to z square by 4 dt, okay, which implies that z star, okay, is equal to z by root of 2 dt. Okay. Once I do that, then C becomes into e power minus z square by 2. Okay. So, this becomes of the Gaussian form. Okay. This becomes of the Gaussian form, and if I do the integral, okay, integral minus infinity to infinity, okay, dz times c of z. Okay. So, this is equal to m by 2 root pi dt, okay, integral minus infinity to infinity. Okay. I can express dz in terms of dz star. Okay. I can express dz in terms of dz star. Okay. Okay. So, this becomes root of 2 dt, okay, dz star, okay, times e power minus z star square by 2. Okay. So, this basically becomes equal to m by root of 2 pi. Okay. The dt will cancel out, okay, in the numerator and denominator, right. Integral minus infinity to infinity dz star e power minus z star square by 2, and you can easily verify that this is the Gaussian function. This whole thing 1 over root 2 pi and e power minus z star square by 2 is the Gaussian function. So, this integral will just turn out to be m, because the Gaussian function is normalized. The integral of the Gaussian function is normalized. Okay. Now, you can also calculate the second derivative. Okay. You can also calculate the second derivative of this. Okay. I am sorry, the second moment, I am sorry, the second moment of this distribution function, to find out what is the spread. Okay. The second moment gives you an indication of how far it is spread. Okay. So, if you recall, I had told you that initially you have a very sharp distribution, and then with time, as the material diffuses, the penetration depth of the material into the fluid increases with time. Okay. And because the total area has to be a constant under the curve, the total mass has to be a constant, the maximum has to decrease as the material spreads, the maximum concentration at the center decreases, and the extent becomes larger. Okay. The extent of this is indicated by the variance or the standard deviation of this distribution. Okay. So, the average, the spread, okay, you can quantitatively express it as the average of z square average, okay, is equal to integral minus infinity to infinity dz z square times c of z. Okay. So, there is the square of the distance from the origin times the concentration at that location. It is called the variance of the distribution. This is an indication of the spread of the distribution. Okay. This is an indication of the spread of the distribution. And we can calculate this variance with respect to time, okay, by just substituting. Okay. Times z square times m by 2 root pi dt e power minus z square by 4 dt. Okay. And I use the transformation z star is equal to z by root 2 dt in this expression. Okay. Kindly correct it here. So, the variance, right. So, the concentration has dimensions of mass, okay, per unit volume. When I integrate that, I get mass per unit area, okay, and multiply by z square, I should get a length square here. Okay. So, this variance is basically this divided by m. Okay. So, the length square is if I multiply the concentration, which is mass per unit length unit volume, dz gives me a mass per unit area times z square, which is mass into length, okay, divided by mass per unit area. Okay. So, this basically has dimensions of mass, because concentration is mass per length cubed, and I have 3 dimensions of mass within the integral, and I divide it by a mass per unit area. So, I get the correct dimension of length in the length square further, which is the same as the left hand side. Okay. So, if I use the normalized distribution, I can divide it by 1. If I use the actual distribution, I have to divide it by m. Okay, I have to divide it by m to get the correct answer. Okay. So, now I substitute z star is equal to z root of 2 dt. So, this will become equal to integral minus infinity to infinity. Okay. I will get a factor out of two dt whole power 3 halves. Okay. And this m and m will cancel out. Okay. And I get in the denominator by 2 root of pi dt, okay, into dz star z star square e power minus z star square by 2. Okay. And this will be equal to, you can verify that you get a 2 dt, okay, divided by root of 2 pi. Okay. You have 2 power 3 halves in the numerator and 2 in the denominator, this 2 power half. I have written this as 2 divided by square root of 2. Okay. I have written this as 2 divided by square root of 2, okay, times integral minus infinity to infinity dz z star square e power minus z star square by 2. Okay. And this whole thing is the second derivative of is the second moment of the Gaussian integral. The second moment of the Gaussian integral, where g naught was defined with a 1 over root 2 pi in the denominator, and integral of x square dx times g naught, that has to be equal to 1. Okay. So, therefore, this spread of the distribution or the variance of the distribution function z square has got to be equal to 2 dt, okay, because everything within that red line is equal to 1. Okay. It is the second moment of the normalized Gaussian distribution, it is equal to 1. Therefore, the spread of the distribution function is equal to 2 dt. So, the average spreads the variance or the square of the displacement from the center, that increases proportional to time. Okay. So, the spread of the distribution increases as square root of t, z square increases as time. So, the average, the square root of z square, that is the standard deviation, sigma will be equal to square root of z square. This is equal to root of 2 dt, that is the spread. Therefore, the extent to which this spreads increases proportional to, okay, square root of t, okay, in this particular case. Okay. So, this variance of the distribution, this variance of the Gaussian function is a way to measure how much the material has spread. Okay. If you recall the initial condition, okay, at t is equal to 0, you can easily verify that this z square is equal to 0 at t equal to 0, okay, because it is proportional to square root of t. So, therefore, the standard deviation is equal to 0. The standard deviation of the distribution is 0 at t is equal to 0. Okay. Recall that I said that we have a finite mass injected into an infinitesimal thickness. Okay. I had said in the last class that we had a finite mass that was injected into an infinitesimal thickness. Okay. Therefore, at t is equal to 0, what we have is that c is equal to 0 for z not equal to 0, okay. Okay, in the configuration everywhere for z not equal to 0. Okay, so, this is the location z is equal to 0, and I have injected material only at this location z is equal to 0. So, for all z not equal to 0, c has to be equal to 0. For all z not equal to 0, c has to be equal to 0. it will be non-zero only at z is equal to 0, and I have the integral condition, integral minus infinity to infinity dz into c of z 0 is equal to the total mass injected per unit area. Okay, it is going to be equal to the total mass injected per unit area. The function that satisfies these two conditions, okay, not with mass m, but rather a normalized mass, okay, a function that satisfies these two conditions, c is equal to 0 for z is not equal to 0, and the total mass is normalized, this is called a delta function. C of z 0 is equal to delta of z. Okay, this is called a delta function. Okay, it is often called the Dirac delta function. Okay. So, the delta function is a function, if I plot, okay, x versus some function f of x. Okay. General functions will have some particular form. This delta function is non-zero only when z is equal to 0. Okay. It is non-zero only when z is equal to 0. It is equal to 0 for z is not equal to 0. Okay. So, it is non-zero only in an infinitesimal interval around z is equal to 0 in the limit as the width goes to 0. Okay. And it satisfies the condition that dz times c is equal to 0. Okay. So, the delta function basically satisfies delta of x is equal to 0 for x is not equal to 0, integral dx delta of x is equal to 1. Okay. And it satisfies another condition that integral dx delta of x times f of x is equal to f of 0. Okay. So, those are the conditions that the delta function satisfies, that is, for all x not equal to 0, this is 0, it is non-zero only at x is equal to 0, but the integral is finite. Okay. And if you multiply the delta function by any function and integrate it, you get the value of that function at 0. Okay. So, basically this delta function picks out the value of this integral at x is equal to 0. So, when the integral is 1, I get the delta function. Okay. When the integral is 1, I get the delta function. Okay. When the integral is m, then I get m times the delta function, delta of z. Okay. So, this is the initial condition, c of z at t is equal to 0 is the delta function times m. Okay. Note this normalization condition for the delta function. Okay. Note this normalization condition for the delta function. Okay. dz times c integral is equal to 1. Right side 1 is dimensionless. On the left side, okay, so yeah. Okay, so, note this condition for the delta function, integral dz times delta of z. Okay. On the right side 1 is dimensionless, on the left side z has dimensions of length, therefore, the delta function has dimensions of 1 over length. The dimension of the delta function is equal to L inverse. Okay. So, that when you multiply it by z, which has dimensions of length, and integrate, then I get something that is dimensionless. Okay. So, that is the dimension of the delta function. Also, in this initial condition, you can verify the left side is a mass per unit volume, it is a concentration. Okay, the left side is a concentration, it is a mass per unit volume. The right side is m times delta, m is a mass per unit area, delta has dimensions of 1 over length, therefore, the right side is also a mass per unit volume. Okay, so, therefore, this is dimensionally consistent. Okay, the left and the right sides have the same dimensions because m is a mass injected per unit area and the delta function is a dimensions of 1 over length in one dimension. Okay, in one dimension this has dimensions of 1 over length. So, to summarize, okay, what we have solved is one dimensional transport, okay, in the z coordinate of the decay of a pulse which was injected at z is equal to 0, okay, the decay of a pulse at z is equal to 0. Okay. So, if I plot the concentration, for example, in another way, if I plot, okay, as a function of z, I plot the concentration. Okay. If I plot the concentration as a function of z, at time t is equal to 0, you are injecting a pulse which has a non-zero concentration only at z is equal to 0. Okay. The governing equation partial c by partial t is equal to d times d square c by dz square with the boundary conditions c is equal to 0 for, since it is an infinite fluid, this is for z going to plus or minus infinity, okay, and the initial condition c of z t is equal to delta of z, okay, at for z is equal to 0. Okay, c of z t is equal to m times delta of z. M is a mass per unit area, delta is dimensions of inverse length. So, this is a concentration. Okay. The solution of this equation is c is equal to m by 2 root pi dt e power minus z square by 4 dt. That is the solution. It is a Gaussian function. Okay. The integral minus infinity to infinity dz times c of z t times z square. Okay. So, this is a constant, it is equal to m, the original mass that was injected per unit area, and the spread of the distribution z square c of z t divided by m, okay, which is the average of the z square, the variance of the distribution function. This is equal to 2 dt. Okay. And you can easily verify that as time progresses, right, okay, as time progresses, okay, at the center z is equal to 0, right, the concentration at z is equal to 0, this z is equal to 0, therefore, the exponential is 1. The concentration is m by 2 root of pi dt. Okay. That is the maximum concentration at the center. Okay. So, what is happening is that as time progresses, okay, the concentration field at early time is going to have a large value and it will be confined to a very thin region. Okay. The extent of spread of this is going to be small. Okay. As time progresses, you get a series of concentrations where the width increases and the height decreases. Okay. The width increases proportional to square root of t. Okay. The width, which is the square root of this, which is the square root of z square, the standard deviation, it increases proportional to square root of t. The maximum height decreases proportional to 1 over square root of t, in such a way that the area under the curve is a constant, which is equal to the initial mass that was injected. Okay. So, that is how it spreads through a series of Gaussian functions whose variance increases proportional to time, standard deviation increases proportional to square root of t, and the maximum concentration decreases proportional to 1 over square root of t. Okay. These are a series of Gaussian functions. So, at the beginning we had made the assumption that it is a delta function. Okay. However, this approximation will also be valid so long as the length scale for the injection, even if I had injected this mass into a finite length, right, For the long time limit, where the characteristic standard deviation square root of dt is much larger than the characteristic dimension of the initial injection, I can still assume it to be a delta function, okay, and do the calculation using a delta function. I will continue this discussion in the next lecture, where we will extend this to 2 and 3 dimensions, and I will just state what are the results obtained. These results can be verified quite easily. I will not go through the derivation in 2 and 3 dimensions here, but since these are exactly very similar to the one dimensional system, I will state the results for 2 and 3 dimensions, and then we will look at some definite problems. So, I will continue this in the next lecture, and I will see you then.